Hi guys, my name is Guy, and today we are going to talk about Newton's method. Firstly, I will introduce about the background of Newton's method. Newton method, as known as the Newton-Raphson method, it is a method proposed by Newton in 17th century in the field of real number and complex field approximation for solving equations. His method differs substantially from the modern method given above. Newton applies the method only to polynomials. He does not complete the successful approximation, but complete a sequence of polynomials, and only at the end arrives at an approximation for root x. Finally, Newton views the method as purely algebraic and makes no mention of connection with calculate. Newton's method was first published in 1685 in a treatise of algebra, both historical and practical, by John Wallis. And in 1619, Joseph Raphson published a simplified description in Analyzed Equationum Universalis.
Hello everyone, my name is Gina. Now I'm going to give you an example of using Newton's method to let you more understand about this concept. Okay, so we're just going to do two iterations of Newton's method. We're going to run doing this twice. So notice that with the function fx equals to x squared minus 8, if you plug in the number of 3, you will get 3 squared minus 8, which is 9 minus 8, you get 1. So you see 1 is pretty close to 0, but 3 is not a root. This is going to be our guess 1. One thing we're going to do next is we also need to compute the derivative, where f dash x equals to 2x, so we got x1 equal to 3. It says to get the next one, so x2, so my next guess is x2 equal to x1 minus fx1 over f dash x1. It says you take the previous one, which is x1, and then we subtract the way we plug into the function, and we also plug into the derivative. We take that ratio and then we subtract it. I'm going to evaluate all this thing. We will get the 3 minus 3 squared minus 8 over 2 times 3, and then we get 3 minus 1 over 6. I'm going to keep this as a fraction. So we got 18 over 6 minus 1 over 6. We got 17 over 6. That will be our second guess, where x2 equals to 17 over 6. So 17 over 6 is a little bit close or less than 3. That was one iteration. We're just going to go back and do this over again. So see, after all this work done, we got 2.828. So we done our two iteration, and we're going to and we got our third guess. Let's even check to see how close are the second guesses. We do plug in f 2.828. We got to the second to the function. We got 2.828 squared minus 8. We got 7.998 minus 8. We got minus 0.02. Again, this is definitely an issue with Newton's method. It does not always work, so sometimes you have to be aware of it, and that sometimes take you far away from the solution. Thank you.
My name is Jen. I'm going to look at the method for approximating solution to equations. So let's see what this application is all about. Let's suppose that we want to approximate the solution to fx equal to 0, and let's also suppose that we have somehow found an initial approximation to this solution, say x0. This initial approximation is probably not all that good, and so we'd like to find a better approximation. And now let's have a look at the graph. The blue line is the tangent line at x0. We can see that this line will cross the x-axis much closer to the actual solution to the equation than x0. Let's call this point where the tangent at x0 crosses the x-axis x1, and we will use this point as our new approximation to the solution. So how do we find this point? Well, we know its coordinates is x1 and 0, And we know that it's on the tangent line, so plug this point into the tangent line and solve for x1 as follows. So we can find the new approximation provided the derivative is not zero as original approximation. Now we repeat the whole process to find an even better approximation. We form up the tangent line to fx at x1 and use its root, which we will call x2, as a new approximation to the actual solution. If we do this, we will arrive the following formula. This point is also shown on the graph above, and we can see from this graph that we will continue following this process will get a sequence of numbers that are getting very close to the actual solution. This process is called Newton's method. Here is the general Newton's method.
Hello everyone, my name is Bowen. I will talk about Newton's method of functions. When dealing with complex functions, Newton's method can be directly applied to find their zeros. Each zero has a position of attraction in the complex plane, the set of all starting values that cause the method to converge to that particular zero. These sides can be made as in the image shown. For many complex functions, the boundaries of their positions of attraction are fractals. Minimization and maximization problem. Newton's method can be used to find a minimal or maximal of a function. The derivative is zero at a minimal or maximal. So minima and maxima can be found by applying Newton's method to the derivative. That is the Newton's method. Thank you for watching.